right, so we are looking at learning objectives 11 through 12 and 13. So learning objective 11 is to determine the limiting and excess reactants in a reaction. Learning objective 12 is to determine the theoretical yields for a reaction, and learning objective 13 is to determine the amount of excess reactant that is left over in a reaction. So we do all three of these all together. Okay, so a few definitions. The limiting reactant gives the amount of product that can form and is completely used up in the reaction. Okay, so what that means is that the limiting reactant essentially goes to zero at the end of the reaction. So the excess reactant. This is the reactant that is left over in the beaker at the end of the reaction. So, limiting reactant problems. They have two things that we're given. So we get two givens. Now, it is easier to use what we call a BCA table to solve these problems. So what the BCA table means is I've got B, which is before, C, which equals to the change. So this is the change that's occurring in the reaction, and A is equal to after. So before reaction, the change in the reaction, and after the reaction. Okay, so problem. If you react 7.99 grams of aluminum with 9.89 grams of hydrochloric acid, A, what is the limiting and excess reactant? B, what is the mass of the excess reactant that is left over? And C, what are the theoretical yields of the products? So steps for BCA tables. Okay, number one, you have to convert to moles of each substance that's given. So I need to convert mass of aluminum, Al, slash HCl, so both of these. And I need to get all of these to moles of aluminum slash HCl. Now, the reason that we need to be in moles is because moles is that counting number, right? So I can't compare my masses of aluminum to hydrochloric acid because the mass of aluminum and the mass of hydrochloric acid are completely different. If they were the same, we can compare the mass, but because they are different, we have to compare in terms of moles. So that is why we have to have moles, okay? So then we are going to go through our moles, right? So I've got 7.99 grams of aluminum. Well, this was the same reaction that I did in the last video. So I know that aluminum is 26.98 grams for every 1 mole. So that's one calculation that I have. I have to have 2 because I've got 2 reactants. Okay. So then I'm going to go to, and you should be able to see this, but then it's 9.89 of HCl times, and again, I already did this, right? So it's 36.46 grams of HCl for 1 mole of HCl. Okay. So then go to my trusty little calculator here. So 7.99 divided by 26.98, that gives me 0.296. And I'm just going to go one more extra significant figure, just so I'm not like rounding too much here. Okay, so 0.2961. This is moles of Al. And then go back to my calculator. 9.89 divided by 36.46. That gives me 0.2713. All right. So I've got 0.2961 moles of Al and 0.2713 moles of HCl. So that's the first step that I need to do. Okay. Again, got to have it in moles so that I can compare the two between the two. Okay, so setting up a BCA table, the only unit that goes in or comes out of a BCA table is the moles. Moles are extremely, 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 extremely important, right? Okay, I'm going to go back to this reaction here because this is the reaction that we're using, right? And I'm going to plug in my coefficients into the top for the reaction part, okay? So that's going to become important just a little bit later, okay? So then I have in my before, so I'm going to kind of go back and forth between the table and my writing that goes below the table, okay? So, and I'm going to start at B, we're going to go to C, and then we're going to go to A, and I'm going to kind of walk you through these steps, right? So at B, you are putting the moles that you calculated in step 1 for the reactants. Now, if that's the only thing that I have in the beaker at the start, right, then my reactants are the only thing that I have, right? So I'm going to put zeros for the products because before the reaction happens, I don't have any of my products, right? So moles that you calculated from step 1 go into B. So then I can go back up here, go to B, and I can go, okay, so this is 0.2961, and this is 0.2713. This is 0, and this is 0, because I have nothing and nothing for those two, okay? So for C, so at C, you are going to put the coefficient from the balanced chemical equation with a x value, just an x. So it's a variable, right? So it's negative for reactants. Think about this. So as we react, we are losing our reactants, right? We are gaining our products. So we gain our products, we lose our reactants, right? So then, and it's going to be positive for the products. So positive products, negative reactants. So then I look at aluminum, right? I've got minus 2x for HCl. I'm going to do minus 6x. For AlCl3, I'm going to be plus 2x. And then for H2, I'm going to have plus 3x. All right, so then that is my setup for the C. And then my after, for my A, I am going to write an equation from B to the before plus the C, okay? So it's B plus C. So then I can go back up here. Well, in my B for AL, I have 0.2961 minus 2x. So I'm just adding these straight down. So 0.2713 minus 6x. And then this is 0 plus 2x, so this is just 2x. And then this is 0 plus 3x, so this is just 3x. Okay, so then there's my setup. That's my table. So then I'm going to, for my next step, I'm going to pick a limiting reactant. And you might be able to figure it out automatically. It's going to give you the smallest x value. So out of your two equations that you wrote for your reactants, solving them and solving for the smaller x value, that's your limiting reactant. Okay, so pick a limiting reactant. And you're going to set that equation to 0. And then you're solving for x. Okay, you can check your answer here by plugging x, the value that you get for x, into the other reactant if your answer is a positive number. You picked your limiting reactant correctly. And if your answer is negative, though, you have to go back and solve for x for the other reactant. You picked the wrong one. Okay, so you picked the wrong limiting reactant. So I'm going to go back up to my table. so that you can kind of see this, okay? So I'm going to look at each of these particular equations here. Now, notice I've got 0.296, which is a little bit larger than 0.2713. So I'm going to say that this is going to be my limiting reactant, right? Just because those mole numbers are a little bit smaller than one. This one's smaller than this one. And then the other thing that I need to look at is my coefficient here. This coefficient is smaller than this coefficient. So definitely like small number divided by that 6 is going to give me that smaller x value. So then I can solve here, right? So x would have to equal to 0.2713 over 6, okay? Now, if you're confused about how I got that, I did 0.2713 minus 6x. That is equal to 0. So then I just pulled the 0.2713 over and then divided it by 6. Okay, so then that is equal to, so my x is equal to 0.0452. And again, I'm going to put one like little extra stick fig there, just because I don't want to round too much here. Now, that number is my x value. So then I can go back and plug in my x value for everything that I've got, okay? So let's go and check my aluminum one, right? So then checking to make sure that I picked the right, limiting reactant, I've got 0.2961 minus 2 times 0.04522. If this gives me a positive number, then I picked my limiting reactant correctly, okay? And my answer is positive, so I definitely picked that correctly. 2057. Okay, so it's picked correctly. I picked it correctly. If that came out to be a negative number, then I would have to solve for x for the other reactant, and that's my x value. If you want to solve for x for both of the reactants and kind of figure out which one is smaller, you can absolutely do that, right? So you're using the smallest x value, right? All right, so then number 4, you are plugging in the value for x to solve for the moles of each substance. Now, we did that with the aluminum one, right? So I'm going to do all of this right here. And for aluminum, right? We did that one already, but let's look at that one again. So aluminum, so moles of aluminum. I'm going to do the 0.2961 minus 2 times x, right? So x is equal to 0.04522. That is going to give me the 0.2057. This is moles of Al. Okay, so for moles of H2, I'm going to do 3 times my x value, which is 0.04522. And that's going to give me 0.3, 0.1. So that gives me 0.1357 moles of H2. Notice I've kind of extended out that sig fig. We'll round to sig figs at the very end of this. Okay, so then moles of AlCl3 is going to be 2 times my x value. 2 times 0.04522 is 0.09044. So again, all of these are moles of of the substances, because anything that goes into my BCA table is moles and anything that comes out of my BCA table is also moles. Okay, so then last step of this whole setup right here. Okay, and I promise if you practice this, it gets easier. All you do are plugging in numbers and like getting all this stuff. It's a lot faster than doing 5 to 10 actual mass to mass calculations. So now, so you're going to convert moles to grams for each substance. So the mass of reactant is the amount of the reactant that's left over, which is my excess reactant. And then my masses of the products are the theoretical yields of the products, or the amount. So like these are the amounts that should form. Okay, so let's look at this. So then if I go back up here, I've got 0.2057 moles of aluminum. So 1 mole is going to be on the bottom. 26.98 grams is going to be on the top. So this is 5.55 grams of aluminum, because I'm going to go back to that 3 sig figs, because I started out at 3 sig figs and 3 sig figs. So I'm going to end with 3 sig figs. Okay. So that's 5.55 grams of aluminum. And then going back up to the top here to figure out how many moles of hydrogen. So I've got 0.1357 moles of hydrogen, and then I've got 0.09044 grams of aluminum chloride. I've got moles of H2. So it's going to be 1 mole H2, and it's going to be 2.02 grams of H2. So hydrogen is 1.01 on the periodic table, plus 1.01 gives me 2.02 grams. Okay. So then that gives me 2.274 grams of H2. Okay. And then the last one, right? So I had 0.09044 grams of AlCl3. I know I'm going to do 1 mole on the bottom. And then I need to calculate the molar mass of AlCl3. And mass of chlorine is 35.45. I have 3 of those, so I'm going to take 3 times 35.45 plus 1 times 26.98 to get my mass of my aluminum chloride. That gives me 97.88 grams. And I can just use my number there that I've got. So I just hit times the 0.09044. That gives me 8.85 grams of AlCl3. All right. So now I can check my answers here. So a really good check to make sure that I am right on all of this stuff is to go back to my my givens, right? So I was given 7.99 grams of aluminum with 9.89 grams of hydrochloric acid. So then go back down to my answers. Okay. I had 7.99 grams of aluminum, and I need to add that to 9.89 grams of HCl. Now, remember, law of conservation of mass states that whatever I had in the beginning of the reaction is the mass that I have at the end of the reaction. So this is my starting stuff, right? Start. All of this stuff is my ending stuff. So then I'm going to subtract out all of my ending stuff. If I equal out to be 0, then I did this problem correctly. I'm taking 7.99 plus 9.89, then I'm going to subtract 5.55, subtract 0.27. I'm going to leave off the 4 there just because I've got 2 places behind my decimal. And then minus 8.85. So I have 3.21. So I did something wrong. All right, so let's try and figure out what I might have done wrong. Okay. I did all my moles right. I did all my things right. Oh, wait a minute. I got grams right here. Number 1, that could be a problem here. Let's check my molar masses here. And the only molar mass that I really had to calculate was this one right here. So let's recalculate that one and see if that may be what I did wrong. Oh, look, up here, 26.98 plus 2 times 35.45. I've got 3 of these, not 2. So that's where I messed up. So 26.98 plus 3 times 35.45 gives me actually 133.33. All right, so I messed this number up right here. So this should be 133.33. Okay, because this all came out to being like a positive 3.21. What? All right, so now let's recalculate this guy. And that gives me 12.1. All right, now let's check this again. So one more check just to make sure that I did this right this time. That is so much better, right? I get negative 0.04. That is close enough to 0. We can say that's 0. That's perfect. Okay, so then that means that I am done. So that was learning objectives. So that was learning objectives 11, which was to determine the limiting and excess reactants. Learning objective 12, which was to determine the theoretical yield of a reaction. And learning objective 13, which was to determine the amount of excess reactant left over. It's all done in one big problem.